Hi, in this video I'll be demonstrating how to safely wire your battery to your inverter. Over here I have an inverter and it's got an AC output for my appliances, but it will need to be connected to a DC source. And over here I have what is a car battery. It's a lead acid car battery. I've got another lead acid battery over here, although it's a smaller capacity battery. And then over there I have a lithium ion battery. Now it's very important that when I do connect batteries to an inverter that I use protection. So in this video I'm going to demonstrate how to use a fuse or a circuit breaker or even both to safely connect my battery to my inverter. There are going to be some technical aspects here in terms of sizing the fuse and sizing the circuit breaker, but I will walk you through it step by step. Now the first thing is to know the specifications of the inverter. So I have obviously specified this particular inverter based on my requirements. Now I only need about 350, 400 watts. Therefore I've chosen an inverter that has a maximum power output of 600 watts. So on the faceplate of the inverter, I can see the maximum power output. There it says 600 watts. And there is the DC input. It says 53 amps, 12 volt DC. So already I can see that this inverter works with a 12 volt source. Right, now this is a 12 volt battery, that is a 12 volt battery, and this is a 12 volt battery. So the first thing is to specify the correct voltage for the battery. Now the next thing is, if I'm using a lithium ion battery, I need to make sure that the inverter has a charge profile for a lithium battery, because a lithium battery charges differently to a lead acid battery. Now this particular inverter allows me to use it with a lithium battery or a lead acid battery. I can select it in the menu here, which allows me to select the charge profile. So in this case, because I can use it with a lithium battery, I'm going to select the lithium battery for this application. Now I need to look at the battery specification. Now, if I need a lot of backup time from my inverter, then I need a battery which can power the inverter for a long period of time. Therefore, I would choose a battery that has a high capacity. So the capacity is shown there. In this case, this is 80 amp hours. This car battery is 100 amp hour. This much smaller battery is only 18 amp hour. So that means that if I use a smaller battery, I'm only going to be able to use my inverter for a short period of time. Now, when selecting the battery, I also need to make sure that the battery can cater for my full load of the inverter. Now, this inverter's full load is 600 watts according to the faceplate specifications. If I had to use the smaller battery, this would be insufficient for a 600 watt load to be used for, say, maybe an hour or 2 hours. So I'm forced to use a battery with a much higher amp hour rating. And that is why I'm going to choose a bigger battery. So very briefly, if I want to see the capacity of this battery, it says 80 amp hours. So I can say 80 amps times 12 works out to be 960 watts. And actually on the sticker here, it says 1024 watt hours. That means I could squeeze out over 1 kilowatt for 1 hour with this battery. So now what I need to do is determine the protection that I'm going to use for this application. Now I'm going to put the battery in a cage so that there's no access to the terminals. And that's the first step in making a safe solution. So I'm just going to put this inside here. So I will have a cover, and then my inverter would probably sit on the top. So just say, for example, it's something like this. All right, so here's the inverter. I've got the positive and the negative. So I need to wire the batteries positive and negative to the inverter. So say, for example, I use this wire. I would wire from there to there, and then the positive I'd wire from there to there. However, I need to make sure that if there's a fault inside here, maybe somebody spills water on it, or maybe somebody connected a microwave oven, whatever, if there's a fault inside here, I need to be able to protect this battery from an overload condition or a fault condition. So that means I'm going to need to use a fuse. There's a fuse here right at the battery, or I can also use this DC circuit breaker in between the battery and the inverter. So because I have this box, I can now mount the circuit breaker on the side of the box so that if the inverter has a fault, the circuit breaker will trip. If I don't want to use a circuit breaker, I can simply just use a fuse in line with the inverter. All right, so I'm going to go through the specifications of the inverter to select a fuse or a circuit breaker or even both. All right, so here are the calculations for the 600 watt inverter. Now, the first thing is I need to have the specifications of the inverter. Now, I do have them. It's 600 watts output is the maximum for this inverter. What's also important is the efficiency, because in order to give me 600 watts on the output of the inverter, I need to know what my battery needs to provide on the input of the inverter. If the inverter is only going to provide me with a 90% efficiency, that means that I take 600 watts divided by 0.9 and I get 667 watts. So that means that the battery needs to provide 667 watts in order to provide me 600 watts on the output. For example, here are the specifications of the inverter. There it says the rated power is 600 watts. It also shows over here the efficiency, but when it's on battery or inverter mode, it is better than 90%. So I've just taken 90% as the efficiency. And I just want to show you another specification, and that is the battery cutoff voltage. The inverter is designed in such a way that if the battery voltage gets below 10.5 volts, and that's for lead, because this inverter can work with a lead acid battery or lithium ion battery. So the low voltage cutoff for lead is 10.5 volts, and for lithium it is 11.5 volts. This is important in determining the maximum current rating, which is important in the design of the protection system. All right, so let's look at the battery voltage for lead acid battery. It's 12 volts, although the float voltage is higher. But once I load the unit, it'll be 12 volts or lower. So let's just look at a best case scenario. Say the voltage of the battery is 12 volts and I need to get 667 watts out of that battery. Therefore, my current is going to be 55.6 amps because power is VI cos phi. And let's just assume that the power factor, the cos phi, is 1. So this would be a DC current. So in this case, I need 55.6 amps from the battery if it is a lead acid battery running at 12 volts. Now, comparing that to the lithium ion battery, and let's just say it's at 13 volts. Lithium ion batteries tend to be at a slightly higher voltage than the lead acid. Now, notice that the current required from the lithium battery is a bit lower than the current required from the lead acid battery. But we need to determine a protection circuit that will cover both setups. So now let's look at under worst case scenarios, because that's what we protect for. We protect for worst case scenarios. So let's look at the battery cutoff voltage. Now, according to the specification, the cutoff voltage is 10.5 volts for lead and 11.5 volts for lithium. Now, I'm going to use the lead because that is a lower voltage, which means that has a higher current. So let's look here. The maximum current with a lower voltage of 10.5 volts is now a higher current because the power output has to remain the same. It's just that the battery has to work harder to give that current. I'm still using 667 watts, but now I'm dividing that by 10.5 volts, and that gives me a current of 63.5 amps. So that is the rated full load input current to the unit when it is providing 600 watts. Now I need to decide, am I protecting for an overload or a fault? And you might be thinking, but isn't an overload a fault, and isn't a fault an overload? An overload may be considered a fault if you designed it like that, but usually a fault has a much higher rise in current than an overload. So let's look at these three graphs. Normal conditions here, 75% of the load. The unit should be able to run like this indefinitely. But now let's look at the peak. So over here, this is 100% of full load. So that would be the 600 watts. For this inverter, it is a 600 watts inverter, so 100% is 600 watts. Now, most electronic devices should be able to handle a little bit of overload. For example, I have tested this inverter and it can go to 650 watts and it still works. So that is an overload. It won't break the inverter, but the inverter is now overloaded. So usually 10% is an overload, 20%, even 30%, depends on the application. But a fault tends to look more like this. Its current is excessive. That's a fault, the red line here. So what we notice with a fault is a very high current that rapidly grows, and it tends to be many times higher than the load current. So the full load current maybe is 100%, but a fault would be 4 times that, 5 times that, 6 times. Okay, but it does really depend on the application. Now I need to decide on the sensitivity of my protection. Let's look at an overload situation. Let's say the overload is only 10%. So that would mean the max load current would be 63.5 amps for 600 watts, but now increased by 10%. So 10% higher than 600 watts is now 660 watts. So the current for 600 watts was 63.5, but now it'll be 69.8 if the unit runs at a 10% overload. Now let's take an even higher overload. Here we have a 30% overload, so it's 1.3 times the full load current. Notice that the current is now above 80 amps. Now that is a much higher current, and we probably find that this inverter would overheat and break. But this is where one needs to know the device that they're protecting. I know that the inverter does have its own internal protection system to stop this from happening. For example, here's the screen of the inverter when I overload it beyond its capability. It does go into a fault mode, cuts off the output, and I have to power down the inverter and restart it, and then it'll allow me to feed my load again. So the inverter does have its own internal protection. So that's very important, because then I can determine if I'm protecting for just overload or am I protecting for faults. Recall earlier that overload is just a little bit higher than the maximum load current, whereas a fault is a much higher multiple of the maximum current. All right, so let's critically evaluate this. Let's call it overload protection. And it's a heavy overload of, say, 1.3 times the full load current, 82.5 amps. So if I wanted to protect for a 30% increase in the full load current, so that would mean 82.5 amps. So let's just call it 80 amps. So if I want to protect against overload, then the protection must cut out the unit at 80 amps. So you might think that let's put an 80 amp fuse in there, but an 80 amp fuse will not cut out the unit at 80 amps. In fact, if I put an 80 amp fuse there, the fuse will allow 80 amps for minutes, even up to an hour. While if I put a circuit breaker there of 80 amps, it'll also allow current to flow for a long time, and it might never ever trip. So I need to look at a lower rated protection device, and I need to base it on the data sheet. So the first question is, am I going to be using a fuse or a circuit breaker, or even both, in something called graded protection? If I am going to use a fuse, then the fuse must be very close to the battery. The problem with a fuse is if the user overloads the unit or there's a fault, then the fuse breaks. Then what often happens is the user does not go and buy another fuse, they just bypass it. So fuse is not ideal. A circuit breaker, on the other hand, allows me to use it repeatedly. So it's unlikely that the user would remove the circuit breaker, because the circuit breaker can be reused. Now, what you could do is also use a fuse and a circuit breaker, but then the fuse must be higher, a higher current rating than the circuit breaker. So only if the circuit breaker does not trip, then the fuse will trip right by the battery. So let's first have a look at the fuse. Now here's an example of a fuse, and let's look at its melting characteristic. All right, so this is the time current characteristic curve for different amperage fuses. Now let's look at an 80 amp fuse. Now the reason why I've chosen 80 amps is because earlier I worked out that if I'm protecting for a 30% overload, the current must cut out at 80 amps. So if I had to use an 80 amp fuse, it's this dotted red line here. Notice that this is 100 amps, this is 90, so this is 80 amps over here. It's this line over here, and it goes all the way to there. Notice that the 80 amp tripping line does not actually cross over the 80 amp load current line. That means that an 80 amp fuse won't melt. Even after 10,000 seconds, it's still not going to melt. So that means I must actually choose a lower current fuse. So let me choose a 60 amp fuse, and there it is, the light blue dotted line. So it's this line over here, and there it crosses. So we're getting a crossing about here. So if I use a 60 amp fuse and the load current is 80 amps, it'll take 200 seconds for that fuse to melt, because that's where the melting line crosses over the load current line. So we can see that even a 60 amp fuse is going to take more than 2 minutes to fuse at the 80 amp load current. So we can see that we have to look at these curves to specify the right fuse size. Now we have to differentiate between normal load and an overload or an unwanted condition, because if I choose a fuse that is too low and the curve is sitting like this, what will happen is that just under normal load conditions, say it's the inverter is running at 500 watts, then we see that the fuse is melting, and that we don't want. So we've got to have a fuse that will melt at a current that is above the normal working conditions, but low enough that it can still cater for an overload if that's what I'm protecting. If you're protecting against overload, well, then you will then look at the overload current. Right, so let's have a look at a circuit breaker. Now, circuit breaker have something called tripping curves, and we get different types of curves, B, C, D. There's actually quite a few, but these are the common ones. Now, what we see here is this is the multiple of the rated current. So this is the current, say I want to protect it for 80 amps, that would be maximum, so that would be 80. Then this would be 160, so it's 2 times the current that I'm referring to. So if I want to go even higher, this is 3 times the rated current. So let's say, for example, I wanted to protect for a current of 80 amps. And if I chose a circuit breaker that is rated at 80 amps, notice that it would actually never trip. So if this is 80 amps, because this is the rated current of the circuit breaker and 80 amps is now flowing, it is an overload on that inverter. Notice that the curve never goes past this axis here. So it'll actually never trip. But if the current, maybe it was double, maybe it was 160 amps, notice that the circuit breaker will now trip much quicker. And if that current was 3 times the rated current, so now we're going to 240 amps, notice that the circuit breaker will trip in less than 0.02 seconds. So we can see that this is dependent on time. And the reason why it's dependent on time is because under a fault condition, the current rises extremely rapidly, and therefore the protection circuit must trip or disconnect that fault as fast as possible, whereas an overload tends to rise slower, or the overload is not anywhere near a fault. A fault tends to be a very low impedance path, like somebody took the output of that inverter and just shorted the leads out together. Somebody took the leads of the battery and just touched them together. That is a fault. Whereas an overload is like putting too many appliances on. So you had one floodlight, you added another floodlight, and now you added your laptop. That's overloading it. But the current does not look like that. It more looks like that. So let's look at a practical example. Okay, let's say, for example, I chose a 50 amp circuit breaker. Notice that a 50 amp circuit breaker is considerably lower than that 80 amp overload current. Now, let's look at where 80 amps sits on this graph. So there's 10 amps, 20, 30, 40, 50, 60, 70. Okay, so it's this red dot here is 80 amps. So if I extend the line, I'm there. Now, notice that the tripping curve has a minimum, and then if I go further up, it's got a maximum. And the reason for that is because there's something called hysteresis in the circuit breaker. The circuit breaker operates within a range or a band. So in the minimum time that the circuit breaker operate will be 50 seconds. But the maximum time, depending on many factors, the temperature, the rate of rise of the current, there's many factors that influence how fast the circuit breaker will trip. The maximum time it will take is, say, about 280 seconds, because there's 100, there's 200, it's almost at the 300 mark, maybe it's like 250, 260. So it's about 50 seconds to maybe 260 seconds to trip. Will it trip for 80 amps? Yes, it will trip for 80 amps, but it will take a bit of time. Now, we don't want the circuit breaker to trip for the inverter just running at full load. If somebody connected full load and wants 600 watts from that inverter, the inverter should be able to provide it if it's a good quality inverter. Now, maybe it won't be able to provide it for 20 minutes, but it should be able to provide it for a bit of time. So we don't want the circuit breaker to trip just for normal load conditions. So let's look at this. Normal load of 600 watts means the current is 63.5 amps coming from that battery. There's 20, 30, 40, 50, 60. I'll put a purple dot on it. So if I extend that line, it's here is the minimum. So it's about 150 seconds. But look at this. This line is in between the maximum and the minimum. So it might never ever trip. That means that if I use a 50 amp circuit breaker, it might trip after 2.5 minutes, but it might never trip. So that means that under full load conditions, there's a chance that the circuit breaker will trip, and there's a chance that it will never trip. But what is rest assured is that at 80 amps, it will trip, although not very fast. It'll trip after 50 seconds to a maximum of maybe 260, 270 seconds. So now here's a 40 amp circuit breaker. I also wanted to trip at 80 amps. Now notice that the tripping time has reduced. It was 50 seconds to 280. Now it's dropped to 40 seconds to a maximum tripping time of 105. Notice how the curve is now more towards the lower current. But now, if the inverter was run at a full load of 600 watts, the unit will trip between 2.5 minutes and 33 minutes. How did I work that out? Because I looked at the full load current, which is 63 amps, which is sitting here, because that's 20, 30, 40, 50, 60. And the purple dot is there, so that's 150, there, 150. And the maximum characteristic line is there, which is 2000 seconds. And if you go even lower, look at a 30 amp circuit breaker. So if somebody puts a load on the inverter that requires 80 amps, it'll trip from 15 seconds to 50 seconds. So within 50 seconds, the circuit breaker would have tripped. However, now we have a problem, because if the inverter is run at full load of 600 watts, the circuit breaker will now trip between 20 seconds and 100 seconds. So that's 0.3 minutes to 1.7 minutes. And why that's a problem is if I connect maybe a laptop power supply or a device that overloads for a short time, or a device that has quite a bit of an inrush current, we might find that the inverter could handle it, but the circuit breaker now trips. And then we're getting something called nuisance tripping, because it's tripping when it shouldn't trip, because the inverter should be able to handle it. So this is the challenge when choosing the circuit breaker. I go back to the initial slide and it says decide on what sensitivity do you want. Are you protecting for just overload? So that means it'll be very sensitive. Just when you overload the inverter, it's going to trip the circuit breaker. Or are we tripping just mostly for faults? Therefore, the circuit breaker will be at a much higher current. So recall that the inverter does have its own internal protection. So I'm not worried about the inverter self-destructing if it's overloaded. I'm not going to use a 30 amp circuit breaker because the inverter's already got its own protection, and I don't want the user to get annoyed with the circuit breaker and remove it. If I choose a 40 amp circuit breaker, this would work if I'm protecting for overload. Now this depends on your selectivity. If you're worried about the inverter, if it's not a good quality inverter, or if it hasn't got good cooling, or if you're worried that the user might damage it, well, yeah, maybe you could use a 40 amp circuit breaker. So for this application, I'm just going to use a 50 amp DC breaker. And the reason is because the inverter already has its own internal protection. I don't want the circuit breaker to trip before the inverter trips. The inverter must cut off the supply as it's designed to do. It is a good inverter, so I'm confident in that. However, if the internal system of the inverter does not trip, at least I know that if excessive current is flowing, after a couple of minutes, it will trip. If the inverter goes into a massive fault condition, it will definitely trip at a fast rate. And I'm also aware that if I run the inverter at full load, 600 watts, maybe I run it for half an hour, it might trip after 2.5 minutes, but judging from these tripping curves, it might not at all. So it's a little bit of a gray area here. Maybe I could have gone to a 55 amp circuit breaker and then it would never trip on full load. But I'm fine with the 50 amp circuit breaker because I have that in stock. And with protection, we tend to always go a little bit lower than higher. Another reason why I don't want to use a 30 amp or a 40 amp circuit breaker is what happens if I connect a floodlight to it or something that has that very high rise in current, that inrush current. I don't want the circuit breaker to keep tripping when the inverter should be able to handle it. Now, keeping in mind that this, again, is based on one's decision. When we design a protection system, we decide at what level we are going to be protecting for. In many power system applications, like your utility supplying your electricity, they would never have protection for just a 10% or 30% overload. Their protection system comes in at a much, much higher fault level because of motors and things like that. So it really depends on the application. Because this is a little electronic device, I'm kind of protecting more in the overload side rather than in the full fault level side. Right, now let's have a look at choosing the correct wire. Now I'm going to specify the cable size from this table over here, which I got from the SANS 10142 standard, and this specifies cables for AC or DC applications, and this will be single core PVC insulated cables, unarmored, and they specify it according to how the cables are run. They've got insulation method 1, 2, 3, 4, and 5 because the current carrying capacity of cable depends very much on how or where the cable has been run. For example, if you just look at a 10 millimeter cable, it should be able to handle 46 amps. That is, if it is enclosed in a conduit in a wall. But notice that that goes up to 57 amps if it is in trunking on a wall, not in a wall. And if it is just clipped, meaning that there's nothing around the cable, we can now go up to 65 amps. So the layout of the cable is very important in how we specify the cable. And also, I'm going to be using copper cable. If it is aluminium cable, you need to derate these or lower these values significantly. Right, so let's look at the current carrying capacity that I need. According to my calculation, maximum load current is 63.5 amps. Now, it's always best practice to specify your cable a bit higher than that. Let's specify it for the overload condition. So that takes it to 70 amps. So that would be the minimum that I would specify this cable. So 70 amps is the minimum. You could, if you wanted to, specify your cable for the 82 amps or 30% full load, but it's unlikely that the inverter will ever work at that current rating. So it might be a bit of an overkill there. The minimum I would say is 65 amps, but I would prefer to go closer to 70 amps. Now, just a note, if your cable is only able to carry 70 amps, but your protection is only set for 80 amps. Now we have a mismatch in terms of the cable carrying current capacity and the protection that will operate. Now, if the protection is only going to operate after 80 amps, then your cable will have to be able to handle above 80 amps. So this is where we need to coordinate the cable size to the protection. That is why it's always best practice to over-specify on the cable size, because we don't want to have a fire because of the cable burning. Okay, so I'm going to look here on this column which says installation method clip direct. Now, it's not going to be clip direct. It's probably going to be more like in free air, but there isn't a rating for this size conductor. So I'm just going to look at this one for now, and I can see that if I use a 10 millimeter cable, whether it is AC or DC, and the two cables are running together, which they will be, I can see that the current rating, the nominal current rating, which means that it should be able to provide this continuously, is 65 amps. So I can already see that that's quite close to the maximum current, but in my case, I would say rather go one size up. So if you go 16 millimeter, you'll have a lower volt drop, which is very important for DC applications. Because the current is so high, we don't want to lose voltage just because of a thinner cable, because it will mean that the battery will have to work harder. But recall from the earlier calculation, if the voltage at the battery is 13 volts, or the voltage coming into the inverter is 13 volts, I only need 51.3 amps. But if the voltage coming into the inverter is a bit lower, look what happens to the current. And that means the battery has to work harder in order to provide a higher current. So what happens is the wire has a volt drop because it has a resistance. So it's always better to try and use a thicker wire. It will actually allow for a slightly lower current. Remember that the load doesn't change. If you need 150 watts, you need 150 watts. So if the voltage at the inverter is slightly lower, it's going to make it up in current. I could even go as high as 25 millimeter, not because I'm worried about the current carrying capacity, but I would now have even a lower volt drop because there's a much bigger cross-sectional area on a thicker cable, which means that I will have a lower volt drop to the inverter. 16 millimeter for me would be the minimum in this application. Right, so now I'm going to install that. All right, so the first step now is to decide if I'm going to use a circuit breaker or a fuse. Now, in this example, I'm going to use the circuit breaker, but I will also just show what to do with the fuse. Now, in order to use the circuit breaker, I'm going to have to cut a hole in this cage or this box that I have here. So on the side here, I've measured the dimensions of the circuit breaker, and then my circuit breaker can fit through there, and I will be screwing it into a frame. So here is my circuit breaker. So all I need to do now is work out the wire lengths. All right, here is my 16 millimeter copper cable. As stated, it's actually better practice if you could use even thicker cable, because the thicker the cable, the lower the volt drop. However, technically, I can use the 16 millimeter cable, and cable is very expensive and it is a very short run. So I'm just going to go ahead with the 16 millimeter cable. Often with the thicker cables, it's quite hard to get the exact colors. So if your cable is gray, for example, you can use insulation tape to just wrap around the cable to demarcate the color. Right, for DC, black is negative and red is positive. So what I need to do now is just cut these to length. This battery comes with these screws to screw into the terminals. So what I do is I measure the screw. The screw is 8 millimeters, so there is my lug. Now on the front there, it actually says 16-8. So it's 16 millimeter wire can fit in there, and the hole here is 8 millimeters. Right, so here's my wire. I'm taking my side cutters here, and I'm not cutting into the copper. What I'm doing is I've close the mouth a little bit, and I'm just going around in a circle here to make sure that I've cut through just the sheath. There it is, and there it comes off. Notice that none of these copper strands came off. If I did this incorrectly, you would see copper strands on the table here. There's no strands on the table. So now what I can do is I take my lug and I put the wires inside there. All of them must be in there. And if it doesn't fit in there, I may not cut that copper. Right, I push that all the way in, and I just need to crimp this. Now you can use a handheld crimper like this. Preferably you could get a more heavy duty one, especially if the lugs are a bit bigger. Right, that is now tight. Right, so this is now fastened. Right, this is just a visual layout of the connection. So I'm going from the lithium battery positive to the input of the circuit breaker. The output of the circuit breaker goes to my inverter. The negative of the lithium battery goes to the other pole of the circuit breaker, and then the output goes to the inverter. Right, here is the DC circuit breaker I'm using. Generally, circuit breakers can be wired from the bottom or from the top. However, with DC circuit breakers, some of them specify that only the positive can be here. Positive input is here and the negative is here, and the output is here and the negative is here. So one has to consult the data sheet for each type of circuit breaker. Now this particular one, I'm going to wire the input over here. So I'm going with the positive from the battery to the input of the circuit breaker over here. And then the negative from the battery would go here, and then the output would go to the inverter. Now, it's very important to prepare the wires coming into the circuit breaker. Now, if I just take these strands and I put it in here, and then I tighten it, even if I tighten it very tight, you might even be able to hear my portable driver here. What happens is the sheer weight of the cable puts pressure on those wires, and then maybe this inverter is driven around and the cable is going like this, and what we find happen is this. It just kind of, it's quite easy to just pop out of there, and anyway, that is no longer a good connection. So what I want to use is a bootlace, but I don't have one big enough, so it would go like that. So I'm just putting a ferrule around mine, and I'm going to crimp it, and then I'll put that in there. If you've got a spade connector, that will also be perfect. Right, so now I can put this in the circuit breaker. And now, even though I move this, none of the strands are coming out of that terminal. Very important, notice that the jacket is not going inside the circuit breaker, it's just the wires. Right, now I'm just inserting the positive. Right, so that's coming into the circuit breaker, and now I'm going to wire the wires going to the inverter. Right, now just do the final tightening with the screwdriver. And it's always good to go and retighten it once more, because the copper seats and it compresses, and then there's always space to tighten it just a little bit more. Right, so I have the battery coming in, and here is to the inverter. So I'm going to mount this on the panel for now. Right, I'm just using this metal bracket here to help me install the circuit breaker onto the box, onto the chassis. So I've drilled these 4 holes here, and now I'm going to feed the circuit breaker from the inside and just screw it in with this little frame holding it in place. Right, so there is my circuit breaker mounted on the unit. Right, that's what it looks like, installed in the chassis. Now I just need to feed these output wires to the inverter. The last step will be to connect up the battery. Right, so I'm just going to wrap these in this protective covering. Okay, so on the inside, there's the wires waiting for the battery. This is the side view. There's the circuit breaker. Here's the output, which is now going to the inverter. So here is the positive and negative, and all I need to do is cut them to size, and then I'm going to wire it into the inverter. Now on the inverter terminals, I also have a screw mount, which means that I can still use a lug. So there we go. It's going to be like that. Right, so I'm just sizing this up. The screw here is 6mm. Right, so I'm just fitting the lug now. When I'm dealing with thicker wires that are joined to terminals that are slightly offset, I only fit the one and then I measure up the other one. Otherwise, we find that the fly lead here is going to be all deformed. So now I can measure this up. Yes, that's right. I'm just putting a cable tie here. Right, so from the circuit breaker, it goes to the inverter. Now, the last step is to connect the battery. So in the meantime, I'm just going to disconnect this so I can get full view of the battery compartment. Now I can put these cables directly to the terminals. Just a few safety precautions before I do that. I make sure the circuit breaker is down. Right, now for the positive lead, we need to put something around here because just now the battery bumps onto the metal or something like that. So the positive lead has to be encased in a resin of sorts. For example, I could put something like this, and then I can put that screw through this top. Therefore, this can never touch the chassis. Now, say for example, you wanted to just use fuse protection. You could put a fuse, and the fuse should be as close to the battery as possible. So in this case, if I was going to fuse this battery, so the fuse would sit like that, and then I would use a nut and bolt on this side. Therefore, if anyone shorts the battery cable, or the inverter has a fault, or the circuit breaker does not trip, the fuse will blow. Can I use the fuse just by itself with no circuit breaker? Absolutely. Just make sure that the fuse rating is low enough to protect the inverter. In this case, I would use a 50 amp fuse for this installation. So if I'm just using a fuse, I would have the fuse here rated at 50 amps. If I'm using a fuse and a circuit breaker, then this fuse has to be rated higher than the circuit breaker. So the circuit breaker is 50 amps, which means this fuse should be 60 amps, or even a bit higher, can be 70 amps. It's best practice to put the fuse on a fuse holder. This could be mounted on the chassis here, and then we'd have the one lead over there, and then just a fly lead going to there, and the fuse sits here in the middle. But in this case, I'm just going to go with the circuit breaker. So I'm not going to be using a fuse as well because the circuit breaker is sufficient. And very important to cover this so that it cannot touch the chassis. So I'm just going to put tape on it for now because this is just for a lab setup. But if you can, get that rubber boot that sits over here. Now I just need to make sure that this battery can't wobble around here. I'm just using some high density foam to stop this battery from moving around. Right, to sum up, I go from the battery, which may or may not have a fuse, into the circuit breaker. From the output of the circuit breaker, it's now ready to go into the inverter. I just need to close this cage. It's good practice to put some heat shrink on the open ends. So I'm just going to insert some heat shrink here. Right, I can just test the circuit breaker. There it's in the on position. Here are the terminals. And if I just short them together momentarily, it should trip that circuit breaker. There we go. And test it one more time. Right. So the circuit breaker is working and it is going to protect that battery. And now I can wire this directly into the inverter. Right, so the circuit breaker is in the on position and I can power up the device. I have my load plugged in. There's no input here, so I'm running completely off the batteries. For my load, I've got these light bulbs, each rated at 75 watts. And then I've got some other nonsense on the floor there, a couple of floodlights, 50 watts, 50 watts, 20, 20. And altogether that summates to just over 600 watts. Now this inverter allows me to measure the output in watts. So there is the output, everything is off, so it's 0 watts. I'm now going to switch things on and the circuit breaker should not trip when it reaches the 600 watts. Right, so my load is now on, there's my floodlights all on. Right, so the maximum output that this inverter can provide is 600 watts. And there we can see that it is fluctuating. One of the loads is a laptop and it is building up the charge in the laptop. Right, so there is the output power. You can see that it is well above the 600 watts maximum rated for this unit. And that's why I said that the protection should not come in if there's just a bit of an overload. There you can see the inverter is actually functioning fine. It's got its own protection and it will cut off if there's a problem. But the circuit breaker is there for a fault or a heavy overload. So there we can see that 620, 630 watts, it didn't trip the circuit breaker. And there it's basically full load and the circuit breaker is still in the on position. And it does go about 10% above. There you can see 660, that's 10% full load. But that circuit breaker will only trip when there is a fault condition, if something is damaged. So it's not going to trip if somebody's overloaded it for a certain period of time, unless I wanted it to do that. If I wanted to protect the inverter from even someone going just even 10% over full load, well then I would have had to have made the circuit breaker a little bit lower in its current capacity. Right, just a tip, the wire from the battery to the circuit breaker should be as short as possible, and then from the circuit breaker to the inverter should also be as short as possible. That will reduce any unnecessary volt drop. Right, there's the circuit breaker, which is now protecting the battery, and I also showed how to use a fuse if you also want to do a fuse protected battery.